this is review video 37, Entropy. So what is entropy? It is the level of chaos or level of disorder in any given system. That could be a reaction system, it could be just a sample of something, but the level of chaos within that sample. Typically, it's represented by the letter S in chemistry, though most often you're going to see it represented as delta S, or the change in entropy in any given system. Our universe tends overall towards increased entropy or increased disorder because to maintain order in our universe requires an input of energy. It requires maintenance, right? Just like if in your bedroom is going to tend toward becoming messy because you're living in it, and it requires effort from you to maintain cleanliness, just like it requires effort to maintain order in the universe. So one good example of that is DNA, the molecule in our bodies that contains all of the information for everything that our body does at all times. DNA is a very long, very complex molecule, and every day our body is expending energy making sure that that DNA is correct, that it stays together and bonded the way it should, folded correctly, winds it and unwinds it, doing what it needs to do. But again, that requires a lot of energy. And when we die, DNA, that really long, really complex molecule, breaks down and decomposes almost immediately, because when we die, our body can no longer maintain that level of order. It can no longer expend energy to maintain that order. And so our body, just like the rest of the universe, tends toward disorder. And once it can no longer put in that energy to maintain order, we decompose. So entropy and reactions. When a system becomes more disordered or more chaotic, we say that it gains entropy. And what that means is that that reaction at that point has a positive delta S value. So a positive delta S value means that a system is becoming more chaotic over time. Reactions with positive delta S values are more likely to happen spontaneously without any extra input of energy. So basically, we know that our universe tends toward disorder because that's the easiest thing to do. It requires the least amount of energy to become disordered. So reactions that become disordered over time, meaning our products have more disorder than our reactants do, those are more likely to happen without any extra input of energy from outside. Whereas when a system becomes more ordered over time, we say that it loses entropy, or it has a negative delta S value. And conversely, reactions with a negative delta S value, reactions that become more ordered over time, they are less likely to just happen naturally or spontaneously because you need to input extra energy to make that happen. So what do I mean by it increases in entropy? Well, several things. Entropy can increase with a lot of things. So chaos increases when we move to a higher energy phase. And higher energy meaning like making molecules warmer, right? So gas is a high energy phase, whereas solid is a lower energy phase. So if I'm going to move from a solid to a liquid or from a liquid to a gas, we would say that we are increasing our entropy as we do that. And the reason that our higher energy phases are more chaotic is because molecules are moving faster. Like imagine you had to sprint around at top speed. That's pretty chaotic. And so the more energy you have, the more chaotic you are. And so you'll see it written out like this a lot. So solids have the least amount of entropy, the least amount of chaos. Liquids have more chaos than solids do. And then gases over on this side have a lot more chaos or a lot more disorder than either liquids or solids do. Chaos or entropy also increases when you increase the amount of moles or molecules of substance present. So the more molecules you have, the more chaotic a sample is. And the reason for that is because the more molecules there are, the more likely they are to hit one another and cause a reaction. So just like when you have more molecules, you are increasing your likelihood of reacting and you're speeding up your reaction, you're also increasing the amount of chaos that is present. Entropy increases with temperature. Faster moving molecules are more energetically colliding, therefore they are more likely to react, therefore they are more chaotic. Entropy increases with volume. If you have a higher volume, what you are doing is you are giving your molecules more space to be in, which means that there are more possible ways for those molecules to arrange themselves, which means you have more chaos or more possible disorder in your system. What units do we use for entropy? 9 times out of 10, entropy is going to be presented to you in joules per mole times Kelvin. You may also see it in kilojoules per mole times Kelvin, and to be honest with you, most of the time you'll need it in this form. So a lot of the times you'll have to convert from this one to that one, which is a very easy conversion to do, but I'm telling you right now, this unit and this unit look very similar to one another, so whenever you're dealing with entropy, you need to pay attention to your units, because if you fail to convert something into this form, then you are likely to get problems wrong because of it. So to convert that way from joules per mole Kelvin to kilojoules per mole Kelvin, all you got to do is divide by 1,000. That's it, because all we're doing is converting joules to kilojoules, and we divide by 1,000 to do that. It's a simple molar conversion. Or not molar conversion, I'm sorry, metric conversion. So, couple of practice problems. Sometimes you'll see problems like this on the AP test where they might ask you which of the following tends toward the most amount of disorder, which of the following has a positive delta S value, or some derivation of that question. So the easiest way to practice that is just saying, okay, well, where is my more chaotic side of a reaction? So looking at this first one, we see that our solid CO2 is moving into liquid phase. We know that chaos increases when we increase our energy of phase. So our liquid product is going to have more chaos than our solid reactant. So this side has greater entropy. We would also say that this particular phase change has a positive delta S value because it is increasing in entropy as that reaction or that phase change proceeds. Looking at this one, we see that we have hydrogen and oxygen coming together in a synthesis to create water. What we know is that chaos increases with the amount of molecules present, or the amount of moles. So when you're looking at a reaction like this, you have to count your moles on each side of the reaction. So over here, I see that there's 2 moles of hydrogen and 1 mole of oxygen with a total of 3 moles on the left side, versus on the right side, we only have 2 moles of water. So what's happened here is we have actually decreased going from left to right, which means that the left side of this reaction has more entropy than the right side. We would also say that this reaction has a negative delta S value because we are losing disorder or gaining order as we move from left to right. Last one, we have this combustion reaction. So there's a couple of things going on with this one because previously in this top one here, the only thing that changed was the phase. So we didn't have to worry about amount of molecules. In the second one, the only thing that was changing was the amount of molecules because all 3 phases were the same. So we only had to pay attention to one thing at a time. However, on an AP question, you're going to have to pay attention to multiple things at a time, just like in this third one here. So what I see overall is that I have gas, 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 liquid. We know that gases overall have a lot more chaos than liquids do. However, the other thing that I'm seeing that's changing is my amount or my moles present. So let's see. On the left side here, I'm seeing 1 mole of gas for my C3H8, and I'm seeing 5 moles of gas for my oxygen, so that's a total of 6 moles, right? However, on the right-hand side, I'm seeing 3 moles of CO2 and 4 moles of water. So that's a total of 7 moles overall. However, since the moles of water are liquid, they count for much less chaos than the gases do. So we can basically ignore that water entirely, meaning that there's only 3 moles of gas on this side, which makes this side of the reaction far more chaotic than this side of the reaction. So we would also say that this reaction has a negative delta S value because we are going to lose chaos when we move from left to right. All right, we've talked about entropy or chaos theoretically, so now it's time to do a little bit of math about it. When we calculate entropy of formation, which is this fun little term right here, delta S sub F naught, we are going to do a very similar formula to the bond energy calculation, except you'll notice that instead of reactants minus products like it was for bond energy, we are going to sum up the products and then subtract the reactants. So from here on out in this class, most things are going to be products minus reactants. Bond energy calculations that we did last week was the only formula that you're ever going to see reactants minus products for. Again, going forward, whenever we see a calculation like this, it's always going to be products minus reactants from now on. But it works the exact same way. You're always going to be given a table like this one. And when you're given a table like that, you'll know that you have to sum up your products, sum up your reactants, and subtract. So this example says calculate the delta SF of the reaction or delta S of formation of the reaction below. And we're given all of those delta S or those S values for each of our reactants and our products in that table. So we take our products, this one, we're going to have 2 times whatever our product is, and that's going to be the SO3, so that's 2 times 257. And we're going to subtract out our reactants. Our reactants are going to be 2 times the SO2, and SO2, according to this table, was 248. And then minus our oxygen, which is 205. And then we just have to plug all of that into a calculator. So give me 1 second to do that. And our answer overall should be negative 187. Now, in terms of our unit, we're going to go back up to our table and check what our unit is. And our unit for this is going to be in joules per mole times Kelvin. If you have any questions about how to do that calculation or anything relating to entropy or the theory or anything like that, please feel free to ask.